Hello students and welcome to Unit 7 Part 1 where we will be learning about systems of linear equations. In this lesson, Lesson 1, we are going to get the introduction to systems of linear equations, and it's going to be a lot of foundational background knowledge focusing on what a system is, how a system of linear equations, which is new, relates to what you already know about linear equations, and also how do we write equations for real-world systems. We will also be looking at how do you check a solution, what does a solution mean, and what are some other key skills that I'm going to need. Well, let's start by defining what is a system of linear equations. Well, think about a system, such as an organ system in your body. It's many pieces working together for a common purpose. Well, a system of linear equations is kind of similar in the sense that it's two or more equations that represent a complex relationship. So far in our studies, we have only talked about singular linear equations, meaning one linear equation that represents a situation. We're just now adding the fact that a relationship is a little more complex and may need two or more equations to represent it. This year we will only focus on relationships with two equations. Now, note, you will be using almost all of the skills that you learned about linear equations to solve systems. So it is going to be building upon things that you know, so you'll be able to make some connections there. So let's start by looking at some of those connections, specifically connecting singular linear equations in general and systems of linear equations. So when we studied singular linear equations, we may have seen a problem like this. Students in Willow Hill can go to Holiday Bowl in Huntington, Pennsylvania to go bowling. Holiday Bowl charges $2.50 per game plus $2 for shoe rental. And when we studied singular linear equations, we would have said, oh, well, X is the number of games you play, and Y is the total cost. And for Holiday Bowl, the total cost would equal $2.50 per, which means multiply, game, which is X, plus $2. So this equation would represent this whole situation, and you can see that it's singular because it only took us one equation to represent this whole situation. Now I'm going to transition to a system. I'm not going to change anything about what we've done so far because systems do have singular linear equations within them. But if we add another couple sentences, we can transition to a system, which means we're going to need more than just this one equation. However, students can also go to Lincoln Lanes in Chambersburg, Pennsylvania. Lincoln Lanes charges $2 per game and $4 for shoe rental. So now we see another equation for Lincoln Lanes. The total cost is equal to $2 per game plus $4. Together, these two can answer a question a student may have. For how many games will the cost to bowl be the same at both places, and what is that cost? Now, we're not actually going to solve this today, we're just getting the foundation. We'll get lots of methods for solving this a little later in the lesson, and then we will practice those methods in lessons to come. But do you see how answering this question involves both bowling alleys, and therefore you would need two equations to represent the comparison between them? So from that sample system of linear equations, we can see that the system is made of more than one linear function and also involves a solution to a question. That question that we were asked, it has a solution, it has an answer. When will it be the same, and what will that cost be? So today's focus skills throughout the rest of this lesson are as follows. We want to know what is a system of linear equations, which we already have addressed. We can kind of check that off our list. But now what we want to focus on, what is a solution to a system? We know that question has an answer. Well, what is the solution? And what types of solutions exist to a system of linear equations? How can we solve a system of linear equations? And there's 5 different ways. We will learn about 4 of them in this unit. And 5, how can I write a system of linear equations for a real-world situation? Which we actually just did, but we'll practice in a little bit. So let's talk about solutions. We have been studying solutions since back in Unit 4 when we studied one variable equations such as 2y plus 3 equals 15. We also studied solutions when we talked about linear equations and we graphed those solutions on a coordinate plane. And we're about to learn about solutions to systems of linear equations when there's 2 or more equations that represent a situation. Even though we're talking about different types of solutions, different solutions to different situations, they're really the same idea. I want you to look for the pattern. When we talked about one variable equation, such as 2y plus 3 equals 15, the solution is the value of the variable that makes the equation true. So for example, for this one variable equation, y is equal to 6, and we can substitute it in to see if it makes the equation true. So 2 times 6 is 12 plus 3 truly makes 15. So indeed, this is a solution because it's the value that makes the equation true. When we transition to linear equations, the solution is an ordered pair or pairs, because we know they have many solutions, x, y, that makes the equation true. So for example, for this linear equation, there are infinitely many solutions, but I listed 4 for us that we can prove work. So the first is 114. 2 times 1 is 2, plus 14 makes 16. Okay, put this one in. 2 times 2 is 4, plus 12 makes 16. Put the third one in, 310. 2 times 3 is 6, plus 10 makes 16. 4, 8. 2 times 4 makes 8, plus 8 makes 16. Now, when we say infinitely many more, we don't mean every single number will make it true, but all the numbers that are on this graphed line will make it true. Now, transitioning to something new. A solution to a system of linear equations is the solution as any ordered pair that makes all the equations true. So for example, the ordered pair 5, 5 makes the first equation true. So if I put 5, 5 here, 5 plus 5 is 10. Is that true? Yeah. But try it here. 2 times 5 is 10. 3 times 5 is 15, and 10 plus 15 is not 28. So 5, 5 only makes the first equation true. This is the ordered pair that will make them both true. 2 plus 8 equals 10. Is that true? Yep. 2 times 2 is 4. 3 times 8 is 24. 4 plus 24 makes 28. So this equation makes all the equations true. So the solution is all about making equations true, whether it's one equation true or more than one equation true, but solutions should make them truly equal to each other. Now, there are different types of solutions. For example, when we solved one variable equation, such as 2y plus 3 equals 5, this is the same information as the last slide, we learned that there could be one solution, just like this example over here, where y equals 6. We also learned that there could be infinitely many solutions. Remember how we take away 2x from each side? And we get 5 equals 5. And we say, oh, that's a true statement, that's an identity, so there's infinitely many solutions. You can put any number you want in there, and it will always be true. But we also had the opposite when there is no solution. So if we take away 2x from each of these sides, we get 5 equals 10, which is false. 5 does not equal 10. That's a contradiction. It means there's no solution. You can try numbers in here all day, and you will never make those two sides equal to each other. So remember, even though we have only one definition of what a solution is, there are three different types of solutions to a one variable equation. Sometimes there's one number that will make it true, sometimes there's any number that will make it true, and sometimes there's no number that you could ever put in there to make it true. Now, when we solved solved singular linear equations such as 2x plus y equals 16, every one of them always had infinitely many solutions, just like this one. The key here, and this will be key in our next lesson, the key to the solutions of a singular linear equation is that all linear equations can be graphed, and the solutions to a single linear equation are all the points on the line. So if I graphed this line in a coordinate plane, it would go through every one of these points and infinitely many more that I could substitute in here and make it true. Now, a solution to a system is more like the types of solutions in a one variable equation, but you can find them by using singular linear equations. There are three types of solutions to systems of linear equations. Sometimes there's just one ordered pair that will make them all true, just like this one could only be made true by 2, 8. Sometimes there's infinitely many solutions, like this one. It doesn't mean every number will make it true, but it means there are too many to list that will make it true. And sometimes there's no solution, and that means that we will never find an ordered pair that can make them both true. We can find pairs that make one of them true, but not both of them. We will talk about why these three types occur and how we can see that on a graph in our next lesson. Now, we're going to get 4 vocabulary terms to describe these types of solutions. The first word is consistent. The word consistent in this case means that the system has at least one solution. At least one. So there could be one or there could be many, but there is at least one ordered pair that we could use to describe this situation. Within the consistent category, there are 2 subcategories. The word independent means that there is exactly one solution. So kind of like our example from our chart, there was only one ordered pair that could ever make that true. Whereas the word dependent implies that there's infinitely many solutions. Here's one, but there are many more that you could choose from. So the options here are to combine them. A system could be consistent and independent, meaning it has one solution, or it could be consistent and dependent, meaning it has infinitely many solutions. So there's 3 of your vocab words, 1, 2, 3. And the fourth is inconsistent, which means the system has no solution. When there's one solution, we call it consistent and independent. When there's infinitely many, consistent and dependent. And when there is no solution, we call it inconsistent.